Well, thank you all for coming to my talk this morning. Today, I'm going to be talking about using Git metadata to predict code bug risk. We've already done the introduction, so we can skip that. So the kind of broad outline of how this talk is going to go is I'm going to start with a brief introduction to Git and some of the metadata that it collects for you. And then in the bulk of the talk, I'll go over how we use that metadata to build the model to predict code bug risk. And then finally, at the end, I'll finish up with a few tips you can use to improve your own Git usage. So first of all, show of hands, how many of you have heard of Git before? Okay. How many of you use Git? Okay, so we can go through the introduction pretty quick then. So first of all, Git is a version control tool, but you already know that because you all use it. So I think the more relevant point on this slide is the XKCD comic on the left, which highlights the fact that most people who use Git do so at a kind of surface level. A lot of times you memorize a couple commands like this is how I add my files, this is how I make a commit, and that's about all you do with Git. And if things break, then you blow it all up and start over. So what I'm going to argue today is that if you go a little bit deeper into Git and learn about some of the other stuff that it's doing under the hood, it's actually a really powerful tool. And in particular, it can be a source of really interesting information about both the history of your code base and your coding practices in general. So that's kind of the main point I'm trying to make here is Git is really powerful, and if you do if you go a little bit deeper than your just git add, git commit commands, you can get a lot of interesting information out of it. The primary unit in Git is the git commit. So this is one unit of change. And a couple things about git commits are particularly relevant for this talk. The first is that each commit gets its own unique identifier. So every commit, you can go back and find that commit by using that unique identifier. And second, each individual commit gets a lot of metadata associated with it. So things like when the commit was made, who made it, what is actually included in the commit. When I talk about using Git metadata, this is the metadata that I'm talking about. All of the information that is associated with each individual commit in your history. So if that's the metadata, if that's the raw material that we want to be using here, how do we go about getting at it? Well, there are three main tools that we're going to be using in this process. Three different Git subcommands. The first of these is git log. Git log shows you the history of changes to your project. So it shows you all of the commits that have been made to your project over the course of its lifetime. And different arguments to git log can expose different parts of that metadata. So you can, for example, just show the commit message, or you can show a little bit more like which files were modified or who made the change. So for example, a simple version might look like this, where you call git log with some arguments and you just get out the commit identifiers over here and the message associated with each commit. So this is a simple just kind of way to look through and see all the changes that happen and the descriptions of each change. You can also use some different arguments and get a little bit more detailed information. So here, it's a different git log call that shows, in addition to the identifier, things like who made it, when did they make it, what is the line. So git log is tool number one, and that's going to be our main workhorse for getting at all of this metadata. But there are a couple others that are also particularly useful. Number two is git diff. What git diff does is you give it two different commit identifiers, two different IDs, and it'll show you all of the changes that occurred between those two commits. So you can give it one point in history and another point in history and see all of the things that have changed within your code base between those two things. So this is an example of what a git diff output might look like. You get the file name, you get the logs, and then you get to see that these lines with the pluses all got added between these two commits. So git log, git diff, and then the last one is git blame. What git blame does is you pass in a file, and it will tell you for every line of code in that file, what was the last commit which modified that particular line. So this is an example output, and over here on the left you can see the commit identifiers, and then the line number, and then the actual code. So for each line of code, you can go back in and say what commit most recently modified this particular file. So these three Git commands are going to be the main tools that we're working with here. Git log to get at a whole bunch of metadata, Git diff to see what kind of changes are being introduced, and Git blame to see what was the last commit that modified a particular line. So that's our whirlwind tour of Git, since you've all used it already. So next we get to the meat of the talk, which is using this metadata to build a model of code bug risk. And this is generally a 4-step process. So step number 1, we need to identify and label which commits in the history of our code base introduced a bug. We're trying to build a model here. We're trying to build a binary classifier. So we need some labels. So step 1 is going to be using Git metadata, track back and figure out these labels, figure out which commits introduced bugs in the first place. Step 2 is build features for each commit. So we're building a model, we need labels and features. Step 1 is get the labels. Step 2 is get the features. Step 3 is to actually train our model, train our binary classifier. Spoiler alert, this is the easiest step, kind of par for the course in machine learning. 80% of the work is getting all your features and labels. And then finally, in step 4, we're going to use one last little bit of Git trickery to set this up so that our model automatically runs and scores every new commit we make to the repository. So that's kind of the 4-step overview of how this model gets built. Step 1 is particularly involved, so we're going to go through that kind of piece by piece. So the main idea here is what we're trying to do is assign labels, figure out which commits introduced a bug in the first place, and we do that with these 4 steps here. So first, we find all the commits that are tagged with a message that includes the word bug or fix. So here what we're trying to do is find all the changes we made to the code base, which were to correct a bug. These are bug fixes. Once we've found those bug fixes, for each of those commits, we want to go in and see which lines of code that bug fix was changing. So we find our bug fixes, and then for each of them, go in, see what lines that bug fix changed, and do that with git diff. Then, once we know what files and what lines that changed, we use git blame to find the previous commit that modified those lines that are getting fixed by the bug fix. And we label that previous commit as having introduced the bug that is being fixed by our later bug fix commit. So one more time from the top, what we're doing is we're looking for bug fixes, seeing what they changed, finding what last modified that thing that they're fixing, and saying the last thing to touch that was what introduced the bug in the first place. Now, this comes with a big caveat that all of this only works if you have very good commit hygiene. So what commit hygiene is the idea that each of your commits should only do one particular thing. So if I have a bug fix commit, a commit that I've labeled as fixing a bug, it should only have changes that are related to fixing that bug. If my bug fix commit fixes that bug, but also changes a couple things over here and tidies up some doc strings that I noticed were bad while I was doing this, then this is going to throw off this whole approach because all of those other changes will get us treated as part of the bug and incorrectly labeled as a bug fix. So 1, every commit should really only be doing one thing. And number 2, your commit messages should be meaningful and standardized. There can be a tendency for commit messages to get sloppy as you go through bug fixes. They start out fixing bug in the labeling thing and turn into that didn't work, try again, and then and then god damn it, and then so on. So you really need your commit messages to accurately describe what you're doing. At the end of this talk, I'll go over a couple tips for improving your own commit hygiene, because even if you're not doing this kind of modeling exercise, it's a useful practice to follow. But for the time being, bear in mind that all of this really relies on this good commit hygiene. So, walking through each of these labeling steps now. First, we want to find commits which fix bugs. So we're going to do that with this git log command right here. Git log, and we tell it to grep to search for bug and for fix, and we pass the -i to make it case insensitive. We tell it to pretty print things on one line because all we really care about is the commit message. And we're also going to tell it to abbreviate the commit just so it's easier to parse. So this will chop the commit identifier down to 8 characters. So at this point, we have a big long list of commits which are fixing bugs. The next step is for each of those commits, we're going to go in and find what lines and what files that commit changed. And to do that, we're going to use this git diff command. So we have some hash, we have some ID for a commit, and we're going to use a little bit of git syntax here, which is this caret. What the caret is saying is, tell me about the commit right before this one. So if we read this git command kind of semantically, it's saying, tell me the difference between the commit right before this hash and then this actual hash. So saying, essentially, what are the changes only introduced by this one commit? Does that all make sense? Looking like one back from where we are now. And finally, the U0 is just saying, only show me the lines that were actually changed in the commit. When you normally run git diff, it'll give you a little bit on either side just so you have some context around the change. But in this case, we only want the thing that was actually changed. So that's the last U0. So that'll get you something that looks like this. Gives you the file name, shows you the code. And in particular, in between these double @ signs, it'll tell you the lines that were changed. So this is what I'm trying to get out of this step. I want to know the file that was changed and the lines within that file. So moving on, once we have that, now we can use git blame to look back in time and see what was the previous commit to modify that line before our bug fix. And that command looks like this. So we git blame, we point it at the file that we care about. Again, we're saying, tell me about the point in history right before my bug fix. So it's that same little caret syntax. And then -l, the start line and the stop line. So this is saying, tell me who is to blame for every line in this file as of right before my bug fix, and especially these particular lines. So an example, here I have before and after applying the bug fix commit. After the commit is applied, you can see that line 187 has a different commit identifier over here. But if we look back to before the bug fix was applied, we can see the commit hash, the ID of the commit that introduced that change in the first place. This is where we're trying to get to this whole time. Because now we know that commit 254E whatever is the one that introduced the change in the first place that our bug fix is now correcting. So we can label commit 254E whatever as a 1. This is a commit that introduced the bug. So that whole process is kind of involved. You definitely don't want to do it by hand, but fortunately, it's very easy to automate that with a bunch of Python. In particular, you can use subprocess.check output and then just pass in your git commands as a string, and that will get you back the response as a string. You do a little Python string processing, some regular expressions and whatnot, and you can repeat that whole process for the entire commit history of your project, of your whole repository. So you can go through for every commit in your history and label it a 1 or a 0 by whether or not it introduced a bug. Okay, that was step 1. But that was the hard step. So from here on out, it's smoother sailing. Step 2, we want to build features for each of those commits. So we have the labels, now we need to build the features. And in this case, git log is going to be our workhorse. In particular, git log with the --stat option, because that gives you an output that looks like this over here. And right off the bat, there are a couple obvious choices or a couple obvious things you can use as features. So for example, how many files did this commit change? That might be an interesting feature. How many insertions, how many new lines of code did this add? How many deletions, how many lines did this take out? With a little bit of creativity, you can also think of, for example, how long is the commit message? If you tag your commit messages, you could build a categorical feature on whether it's an enhancement or a bug fix or a refactor or something like that. Did this work happen on the weekend? Did this work happen after 11 p.m.? All these kind of things you could make. And if you really want to make friends, you could build a commit or a feature on who made it, but use at your own risk. So anyway, step 2, got our features. Step 3, again, it's the easy one. In this case, we used a random forest classifier, built a model on these features and labels, and it kind of works. So we get an AUC of 0.76, which is really not that bad. We can look at some of the feature importances in just a simple model. Length of the commit message shows up on top for most predictive. Additions, deletions, time actually does turn out to be kind of predictive here. So yeah, once you've done all the work to build up your labels and build up your features, building the model kind of works. But here I'm going to rain on the parade a little bit and repeat the caveat that this really absolutely requires that you have really good commit hygiene. So the example I'm showing here is from running this on kind of our most pristine internal repository and trying it on things where the coding standard and the process standard is a little bit lower. Really degrades the performance. 1, in terms of the model, and 2, in terms of how much you should trust the model. Like being able to duplicate the labels, if the labels aren't meaningful, isn't particularly useful. So big warning, this really, really requires good commit hygiene. And then the last step is to hook this up so that it runs automatically every time you make a new commit. And to do this, we're going to use one last little bit of Git, which is called Git hooks. So Git hooks are scripts that run automatically every time you take a particular Git action. So for example, you could have a pre-commit hook that runs before, like you're trying to make a new commit, but before it gets saved, before it gets recorded, this pre-commit hook script will run. There's another one for commit message, which every time you try to save a commit message, that hook will run. And the one that we care about is the post-commit hook. So every time you make a new commit and record it, this post-commit hook script will run. So what you can do is make a simple little Python script, put it in your project.git/hooks in a file called post-commit, and this file will run every time you make a new commit. So what you can do is pull in a few packages, check the output of your latest Git log call. The --1 means only tell me about the most recent one commit. Do whatever feature parsing you did in the first place to generate your model. Load up your pickled model and predict on the features of your most recent one. So big drum roll, the final output of all of this is something that looks like this. You make a new commit and you get a little thing that says, this is how risky this particular commit is. So that's kind of the bulk of the talk. That concludes the modeling portion, but before I wrap up and open up for questions, I want to quickly run through a couple things you can do on your own to improve your commit hygiene, not just because you might want to do this kind of modeling exercise, but because it's useful in general. So I say it's useful in general. Why is that the case? Well, number 1, clean commit histories can help you understand the evolution of a code base. Say you go on vacation for 2 weeks, you come back, you want to see what happened. If your colleagues use good commit hygiene, you can just pull up the repository, see the messages, see what's been changed, see what's been worked on, at a glance, see what's going on in the code base. That's very handy. Number 2, maybe even more handy, if you have good commit hygiene, every single line of code in your code base is documented. Because if you come upon a block of code that you don't understand and there's no inline comment, you can pull up, you can like git blame, see what commit introduced that, Git logs, go find those commits, go find every commit that touched those lines and see what introduced it, how did it get changed, why did it get changed, and you can do that for every single line in your code base if you have good commit hygiene. And finally, it's not that hard. Git has a couple tools that make it even easier, so I'll go over those real quick and then we'll be done. First of all, there's that commit message hook that I mentioned before. This runs every time you try to save a commit message, so you can do some very simple checking here. Just make sure the commit message is of a certain length, not just fix or bug or damn it. You can also enforce standards around tags. So if you use tags for your commits in your repositories, for like a bug, a test, a work in progress, things like that, you can automatically reject commits that don't include that tag in their commit message. So that's one easy step. What about the situation where you've gotten carried away and made a whole bunch of edits to one particular file that aren't all necessarily related to the same thing. Well, git add has this handy patch option, which lets you independently select edits to a file and add them in separate commits. So what it does is you git add with this patch flag, and it will present you each little block of changes that you've made, and you can choose whether or not you want to add that particular block of changes. So that's pretty handy. And finally, what if you've already made a whole bunch of messy commits? Well, in this case, the interactive rebase is your friend. So what interactive rebase lets you do is go back and edit your commit history. You can take individual commits and break them up. You can combine previous commits into one bigger one if you have lots of little things that are all doing the same general task. You can change commit messages, all that kind of stuff. Git rebase is super powerful, but I will end with one warning, which is you should only rebase code that other people haven't seen yet. If you're just working on your own branch, your own fork, rebase to your heart's content, but once other people have started working off your code, you shouldn't be rebasing. Rebase is its own thing, so I won't get into it any more than that. I think that's time anyway. So with that, I'll thank you for your attention and open it up for questions. Yeah.
Did you run any modeling for your, excuse me, did you run any modeling for your feature selections? I know you're making that joke about whether you want to pick the person as part of a feature, but.
No, so this is kind of in the proof of concept stage, so we haven't done any elaborate feature engineering or model tuning or anything like that. It was really just kind of see if this works stage.
Did you ever try using Git bisect to be more accurate about where the bug came from?
The question was, did I ever use Git bisect to be more accurate about where the bug came from? No, I didn't.
Could you modify your approach to handle bugs that are introduced over a series of commits, especially when it's a complex piece of code?
I think that would be kind of hard to do because of the way we're actually doing the labeling in the first place. So that is, that's a fair point, and that's definitely a limitation of the approach as it is here.
Have you experimented with tools that, or integrating with tools that measure test coverage?
Can you say a little bit more about what kind of integration you mean?
Oh, sure. Thinking of a tool like CodeCov that will tell you which lines of a file are covered by a unit test?
I hadn't considered doing that.
Can you say something about model interpretability? So your number one feature was length of the commit message. Does that mean it's unusually short commit messages or unusually long commit messages that cause the problem?
Yeah, it's so we're using a random forest, so we can't automatically infer directionality from the feature. We had a couple competing internal hypotheses. One was that long commit messages mean complicated changes, which are more likely to introduce bugs. The other was that short commit messages were proxies for kind of cowboy coding. So with a little more work, you could dive into that question, but that's kind of the general answer for model interpretability. If you have a random forest, you need to go do other things than just look at the feature importances.
Just right off that, given that the next two were additions and deletions, wouldn't that imply that it's just big commits classified?
Yeah, that does seem like a reasonable interpretation.
Have you done any testing on this model on a different project to see how generalizes?
Oh, how transferable the model is?
Yeah.
I didn't try taking the same trained model and applying it on different code bases. We did give a little thought to, within the feature engineering, you could have kind of project-specific features if there's one project you really care about. So, problematic, one file has a lot of the complicated logic. You could just have a binary on, was that file modified? But we didn't try taking a trained model from one project and porting it over to another project.
Do you know how many bug fix commits we would need before we would get to see reasonable results from this, or how many you had in your project?
So this project had order 1,000 commits or so, and I want to say there were order 100 bug fixes. I can't really give you, that's my only data point. We tried it on this, and this is what we got with this. I'm not sure how it would perform if you tried it on sparser data.
We have time for one more question. Anybody else? No? Okay, thank you, Henry.
Thank you.
Everybody give him a round of applause.